out between Mars and Jupiter, something very odd is happening. An interstellar visitor, the object we now call 3I/Atlas, is flaring, twisting, and shedding material in ways that look nothing like the calm, textbook comets you're used to seeing. New images from both amateur telescopes on Earth and NASA spacecraft across the solar system have revealed an object that seems structured, restless, even organized. Not because it's breaking physics, but because it's forcing us to use all of physics to understand what's going on. Welcome back to Galactic Briefing, where we unpack the real science behind the biggest stories in the cosmos. Today, what these new 3I Atlas images actually show, why some people are whispering about artificial objects, and what scientists think is really happening. 1. Meet 3I/Atlas, the third interstellar visitor. 3I/Atlas is only the third confirmed object we've ever seen that came from outside our solar system, after 1I/Oumuamua in 2017 and 2I/Borisov in 2019. It was discovered in mid-2024 by the Atlas Survey in Hawaii as a faint, slow-moving object on a highly hyperbolic path, the telltale sign that it isn't gravitationally bound to the sun. Its orbit says, this thing came from the stars, is just passing through, and will never return. A few reasons 3I Atlas instantly became a celebrity. It's brighter and larger than Oumuamua, which stayed frustratingly small and mysterious. It passed the sun in late October 2025 during a solar maximum when the sun is hurling out powerful flares and coronal mass ejections. It's now moving into a geometry where, from Earth's point of view, we can watch sunlight and solar wind carve complex features into its coma and tail. NASA took this seriously enough to organize a multi-mission observing campaign and held a dedicated science briefing on November 19th to share early imagery from spacecraft at Mars, in Earth orbit, and elsewhere in the solar system. So what did everyone see that caused such a stir? 2. The strange images that lit up the internet. Amateur astronomers can be ridiculously good these days. Using mid-sized backyard telescopes, long exposures, and careful image stacking, some observers captured 3I Atlas as a bright, structured object, often more vivid than the background stars in their frames. In their raw sequences, taken minutes apart, the comet didn't look like a soft ball of fog. It looked alive. Its outline stretched and twisted between frames. Faint structures in the coma seemed to rotate or shear across the image. The tail didn't stay as one smooth fan. It showed thin, sharp filaments, sometimes bending in slightly different directions. Stack those frames into a time-lapse, and it looks like the whole object is spinning quickly, with dust jets sweeping around like the blades of a slow-motion sprinkler. That's where the more dramatic claims began. It's rotating in minutes. The jets look too organized to be random. Is something steering this thing? At the same time, Harvard astrophysicist Avi Loeb and collaborators highlighted professional images that show multiple narrow jets, a strong main tail, and even a sunward anti-tail, structures that really do look unusually crisp and complex for a distant comet. So what's going on here? Is this a natural comet behaving at the extreme edge of what physics allows? Or something else? 3. Why 3I Atlas looks so engineered. Let's break down the weird features one by one and compare them to things we already know comets can do. A. Multidirectional jets. Comets are not smooth snowballs. Spacecraft that visited comets 67P, Temple 1, and others showed rugged surfaces with cliffs, pits, and cracks. Gas vents erupt from specific spots as sunlight heats subsurface ices, forming jets that can shoot hundreds of kilometers into space. So multiple jets emerging in different directions? That's actually normal if the nucleus has many active patches and is rotating. What makes 3I Atlas look different is the jets appear unusually narrow and collimated in some images. They may be strong compared to the total coma, making the structure stand out visually. Some jets seem to point in directions that don't line up with the simple everything blown straight away from the sun picture. But again, we've seen complicated jet geometry before. The Rosetta mission watched Comet 67P's jets flicker on and off as the comet rotated, creating very intricate fan-like structures around the nucleus. 3I Atlas is doing the same kind of thing, just with the added twist that its composition and spin are not what we're used to. B. The sunward antitail. One of the most dramatic features in the new images is a bright, skinny structure pointing toward the sun instead of away from it, an apparent violation of comet tails always point away from the sun. Sounds impossible until you remember perspective. Comets can show what's called an antitail, a tail that appears to point sunward from Earth's point of view, but is really a sheet of dust laid out along the comet's orbit. When Earth crosses the comet's orbital plane, that sheet can line up almost edge-on, creating a narrow spike that seems to aim toward the sun. So the antitail is weird-looking, yes, but it does not break physics. It's a sign that ATS is shedding a lot of dust along its orbital path, and the Earth-Comet-Sun geometry is just right to turn that dust into a sharp, sunward line on the sky. C. Rapid changes and apparent fast spin. This is the part that has people most excited. Visible shape changes over minutes. Most comets spin with periods of hours to days. As they rotate, different jets come in and out of sunlight, so the pattern of gas and dust evolves. On short timescales, though, we usually only see subtle changes. With Atlas, some image sequences seem to show the coma stretching or skewing in a new direction over a few minutes. The brightest jets lighting up new angles between frames. There are three big caveats here. Processing effects. Long exposures and aggressive contrast stretching can make small shifts in brightness look like big morphological changes. Stack alignment, seeing conditions, and noise can all exaggerate apparent motion. Jet flickering. Even without impossible rotation speeds, jets can flare up and fade as local vents open, clog, or get shadowed. That can shift the center of light, tricking the eye into seeing a global spin. Unknown rotation period. We don't have yet a precise, widely agreed upon spin rate for 3I Atlas. Early estimates and light curve attempts are still being refined. Until we have clean photometry over many nights, claims of minute-scale rotation are more impression than measurement. Could Atlas be rotating faster than a typical comet? Perhaps on the order of tens of minutes or less? That's not impossible. Small solar system bodies can spin very fast before centrifugal forces start ripping them apart. But we need careful data, not just dramatic animations. 4. Natural thrusters and non-gravitational acceleration. One of the genuinely fascinating things about 3I Atlas is how jets can act like thrusters. When gas vents from one side of a comet, it exerts a tiny push, a rocket effect. For many comets, this creates measurable non-gravitational acceleration. Their paths through space deviate just slightly from what gravity alone predicts. This was famously seen in Oumuamua and in several dark comets with strong outgassing and weak comas. For Atlas, the multiple jets and complex tail actions are exactly the kind of activity that could produce sideways pushes. That in turn can alter its orbit by tens or hundreds of kilometers per day near perihelion, small in cosmic terms, but large enough to be measurable. From far away, that can look like the object is steering itself. In reality, you don't need alien engines for this. You just need lots of volatile ices buried at odd angles, a nucleus with an irregular shape, and some light that turns those venting regions into a messy but perfectly natural network of tiny thrusters. That's still incredibly cool physics, even if it's not science fiction. 5. So, could it be artificial? Whenever we see an interstellar object doing something unexpected, the same question comes up. What if it's not a rock? Oumuamua triggered that debate first. Its elongated shape, lack of obvious coma, and small unexplained acceleration led a few researchers, including Avi Loeb, to speculate about artificial origins, like a light sail or a fragment of alien technology. Most scientists now think Oumuamua was a very...
Neptune isn't exactly where it's supposed to be. Not by much, just the tiny drift, measured over decades, but enough that the math that's worked perfectly for 170 plus years doesn't quite line up anymore. Astronomers have checked the usual suspects: the planets, their masses, Saturn's rings, the sun's pull, and something is still off. Whatever is tugging on Neptune is invisible. And one of the wild possibilities on the table is that the sun might have a tiny black hole as a distant companion. Let's unpack how we got here, what Planet 9 is, why some people suggest a black hole instead, and what the next few years will likely reveal. 1. The first time a drifting planet changed everything. We've actually been in a situation like this before. In the 1800s, astronomers realized Uranus wasn't following the orbit Newton's laws predicted. It was being pulled slightly ahead of where it should be. Two mathematicians, John Couch Adams in England and Urbain Le Verrier in France, did something audacious. They assumed an unseen planet was disturbing Uranus, then worked backwards from the tiny orbital errors to calculate where that hidden world had to be. In 1846, a telescope in Berlin pointed exactly where Le Verrier's math said to look, and boom, Neptune was sitting less than a degree from the predicted position. Gravity plus careful measurements had literally summoned a new planet into existence. Today, we may be in a similar situation, only now Neptune is the one not behaving. 2. Tiny anomalies, huge implications. Fast forward to the 21st century. NASA's Cassini spacecraft spent 13 years orbiting Saturn, acting not just as a camera, but as an ultra-precise test mass. By tracking Cassini's trajectory, scientists pinned down Saturn's position and gravity field with ridiculous accuracy. That information feeds into detailed models of the whole outer solar system. When those refined models are compared to real observations of Saturn, Uranus, and Neptune, a pattern emerges. Their calculated positions and their measured positions differ by small but consistent amounts. The discrepancies grow over time instead of averaging out like random noise. For Neptune in particular, its orbit seems to be ever so slightly off, as if there's an extra gravitational pull that isn't accounted for by any known planet or by the sun alone. On their own, these are tiny effects, but this is exactly how the story of Neptune began with Uranus. Minuscule orbital errors that pointed to something big. So what could be tugging on Neptune? 3. Planet 9, the hidden giant. The leading idea for almost a decade has been Planet 9, a large, distant world orbiting far beyond Neptune. The Planet 9 hypothesis originally didn't come from Neptune's drift. It came from strange patterns in the orbits of very distant icy objects in the Kuiper Gulf and beyond. Some of these extreme trans-Neptunian objects, or ETNOs, have long, stretched-out orbits. Their closest points to the Sun, perihelia, tend to point in roughly the same direction in space. Their orbital planes are also tilted in a surprisingly similar way. Randomly, that alignment should basically never happen, The early analysis suggested odds of less than 10,000 in 1 that this is just a coincidence. Simulations showed that if you place a big planet, maybe 5 to 10 Earth masses, hundreds of AU from the Sun on an elongated, tilted orbit, its gravity naturally shepherds those distant objects into the clustered pattern we see. That hypothetical world became Planet 9. If such a planet exists, it would also gently perturb Neptune's orbit over long timescales. Some detailed models show that a Planet 9-like object could produce deviations in Neptune's position of roughly the size we observe, depending on where it is along its orbit. That's the nice, tidy version. Neptune's orbit is weird. Distant small bodies are weird. One big hidden planet explains both. But the universe rarely stays tidy for long. 4. The problems. Missing planet, messy data. There are 3 big issues. 1. We still haven't seen Planet 9. Teams have scanned the predicted regions of the sky with powerful telescopes, and nothing obvious yet. If Planet 9 is there, it's either fainter than expected, smaller, darker, or farther, or hiding in a region of sky that's hard to survey, crowded star fields, low galactic latitude, etc. 2. The Kuiper Belt clustering might be partly an illusion. Large surveys like OSSO and the Dark Energy Survey argued that once you correct for where and how we've actually looked, the alignment of those distant objects is less dramatic, maybe even consistent with chance. That weakens the original Planet 9 case. Newer work with larger samples does still find structures that Planet 9 can explain well, but the debate is very much alive. 3. Neptune's anomalies are small and multi-cause. Even if Planet 9 exists, it may not fully explain Neptune's drift. Other subtle effects, like the combined gravity of many small bodies in the distant Kuiper Belt or tiny mismodeling of planetary parameters, may also contribute. So astronomers started asking, what if the tug is real, but Planet 9 is something stranger than a normal planet? 5. The black hole idea. Here's where things get wild. In 2019, 2 physicists, Jacob Schultz and James Unwin, suggested a radical twist. Maybe Planet 9 isn't a planet at all, but a primordial black hole, a relic from the early universe that our sun captured long ago. A primordial black hole with a mass 5 times that of Earth would be only a few centimeters to a few tens of centimeters across, roughly grapefruit scale, emit no visible light, act gravitationally identical to a planet of the same mass on the same orbit. From the point of view of Neptune and the Kuiper Belt, it doesn't matter whether there's a frozen super-Earth or a tiny black hole out there, gravity is gravity. Why even consider this? Because gravitational microlensing surveys, which look for brief brightening of background stars when a compact massive object passes in front, hint at a population of unseen planet-massive objects drifting through the Milky Way. If some of those are primordial black holes, the odds that the young sun might have captured one aren't zero. If such a black hole were now in a wide orbit a few hundred AU away, it would tug on Neptune and the outer planets, sculpt the orbits of distant icy bodies, and remain completely dark in optical telescopes. To test this, scientists look for indirect signals. A black hole should sit inside a halo of dark matter. Collisions of dark matter particles could produce gamma rays. If Planet 9 is a black hole, there might be a faint gamma ray glow from its region of the sky. So far, no convincing detection, but searches continue. Is this scenario likely? Most astronomers would say it's very speculative, but it's one of the few ideas that naturally explains an invisible, massive thing in a wide orbit. Or maybe it's not a single object at all. There are other possibilities that don't require a 9th planet or a black hole. A massive unseen disk, the ZM belt. One idea is that the outer solar system contains a broad disk of countless small icy bodies, more mass than we currently account for, whose collective gravity shapes the orbits of extreme objects and tugs slightly on Neptune. Instead of one big shepherd, Planet 9, you'd have a whole crowd gently pushing and pulling on each other. Over millions of years, this disk could self-organize and naturally produce some of the orbital clustering we see, through processes called inclination instabilities. The catch, to have enough mass, that disk should produce many more detectable objects than we've seen so far, unless it's farther, darker, or composed of smaller bodies than we expect. B. Many smaller mini-planets. Another variant, instead of one super-Earth, maybe there are several Mars-sized worlds at a few hundred AU, each too faint for current telescopes. Together, they could sculpt the Kuiper Belt and shift Neptune's orbit. That's even harder to test individually, but upcoming surveys might start to rule this in or out. C. Gravity itself might need a tweak. Then there's MOND, Modified Newtonian Dynamics, a theory originally invented to explain galaxy rotation without dark matter. MOND changes how gravity behaves at extremely low accelerations. A recent study by Catherine Brown and Harsh Mathur asked if MOND is right, what would it do to the distant solar system? Their calculations show that MOND's extra weak pole, always roughly toward the Milky Way's center, could, in principle, account for some of the orbital quirks of distant Kuiper Belt objects and the slight anomalies in Neptune's orbit. Most physicists are skeptical. MOND has trouble fitting with broader cosmology and general relativity. But the fact that a galactic-scale tweak to gravity happens to match parts of the solar system data is unsettling. 7. The Rubin Era. We're about to get answers. Right now, we're in the messy middle of the story. Data says something is a bit off in the outer solar system. Several hypotheses can explain different parts of the puzzle. None has been decisively proved or killed. The big game changer is the Rubin Observatory in Chile. Rubin is designed to scan the entire southern sky every few nights, catching anything that moves, from near-Earth asteroids to distant slow drifters in the outer solar system. Over its 10-year survey, Rubin is expected to discover tens of thousands of new trans-Neptunian objects, sharply reduce observational bias in where we've actually looked, refine the orbital statistics enough to tell whether the clustering is real or a selection effect, either spot Planet 9 if it's a conventional.
We're talking about Avi Loeb, a theoretical physicist at Harvard and head of the Galileo project. He's one of the most vocal voices asking NASA for more transparency and more data on 3I Atlas, the mysterious third interstellar object to pass through our solar system. In this interview, he's asked a simple question. NASA is convinced it's just a comet. Are you convinced? His answer is basically, it's not about what NASA says. The verdict should come from the data, and the data, according to him, is weird. A tail pointing the wrong way. Loeb focuses on NASA's own best image of 3I Atlas from the press conference. In a normal comet, gas and dust are pushed away from the sun by sunlight and solar wind, so we expect the main tail to point roughly away from the sun. But that's not what this image shows. Instead, he says, there's a feature extending in the direction of motion ahead of the object, not simply away from the sun. That's strange. If it were just ordinary outgassing, the flow of material should behave like every other comet we've studied, pushed back by sunlight, trailing behind or away from the star. So Loeb asks a provocative question. Is this just natural gas being blown around in a weird way? Or could it be something more exotic, like a beam of light or particles projected ahead of the object? We're talking about Avi Loeb, a theoretical physicist at Harvard and head of the Galileo project. He's one of the most vocal voices asking NASA for more transparency and more data on 3I/Atlas, the mysterious third interstellar object to pass through our solar system. In this interview, he's asked a simple question. NASA is convinced it's just a comet. Are you convinced? His answer is basically, it's not about what NASA says. The verdict should come from the data, and the data, according to him, is weird. A tail pointing the wrong way. Loeb focuses on NASA's own best image of 3I/Atlas from the press conference. In a normal comet, gas and dust are pushed away from the sun by sunlight and solar wind, so we expect the main tail to point roughly away from the sun. But that's not what this image shows. Instead, he says there is a feature extending in the direction of motion, ahead of the object, not simply away from the sun. That's strange. If it were just ordinary outgassing, the flow of material should behave like every other comet we've studied, pushed back by sunlight, trailing behind or away from the star. So Loeb asks a provocative question. Is this just natural gas being blown around in a weird way? Or could it be something more exotic, like a beam of light or particles projected ahead of the object? He imagines a scenario where such a beam might be used to clear micrometeorites out of its path as it travels, not as a claim, but as an open question. For him, this pattern raises more questions than answers. The coincidence with Jupiter. Then, Loeb brings up something new he noticed from fresh orbital calculations. According to those numbers, on March 16, 2026, 3I/Atlas will pass very close to Jupiter. Not just kind of close. He points out that it will be at almost exactly the distance where Jupiter's gravity starts to dominate over the sun's gravity on the object. In other words, the comet will be positioned at the perfect distance for Jupiter to strongly control its path. To Loeb, that is a remarkable coincidence. He suggests that a slight non-gravitational push, the kind already reported in the object's motion after it passed closest to the sun, would be enough to adjust its path just enough to hit that sweet spot near Jupiter. So he starts asking, why is this object so precisely on course for that ideal gravitational distance from Jupiter? If an advanced probe wanted to release something near Jupiter, say devices, instruments, or probes, wouldn't that be exactly the kind of trajectory you choose? He's not saying this is alien tech. He's saying the coincidences are piling up. 3I/Atlas is very massive, far more massive than the previous interstellar objects. Its trajectory lies right in the plane of the planets, a very specific alignment. It will pass Jupiter at just the right distance for Jupiter's gravity to take over. These are the anomalies he thinks NASA's not addressing seriously enough. Learn from anomalies, don't dismiss them. The host reads a sharp quote from Loeb's own writing. Imaginative scientists master the humility to learn something new from anomalies, rather than display the arrogance of expertise. In plain language, real science means staying humble when the universe behaves strangely. Instead of forcing everything to fit old explanations, you look at the weird data and ask, what is this trying to tell us? Loeb feels NASA is too quick to close the case and call it just a comet, without deeply engaging with the strangest aspects. How unusually massive 3I/Atlas is compared to what we expect to see entering the inner solar system once per decade. How neatly its path fits within the plane of the planets, instead of some random angle. How precisely it's heading toward that critical distance near Jupiter, where the gas giant's gravity dominates. For him, each one of these is a red flag that says, don't be so sure. Look again. 7 jets, natural thrusters, or something else. At the end of the segment, the interviewer asks Loeb, when 3I/Atlas comes closest to us, what specific measurements would he most like to see? His answer, the jets. Recent images from amateur astronomers show at least 7 distinct jets of material coming off of 3I/Atlas. This is gas being shot out into space from different points on the object, like a multi-nozzle fountain in the dark. Loeb wants to know 2 key things: the speed of those jets and the composition of the gas inside them. If the jets are moving at speeds consistent with ordinary comet outgassing, sublimation of ice driven by sunlight, then a natural explanation fits. But if the gas is moving much faster than expected, if the speeds are more in line with engine-like exhaust rather than slow sublimation, then, he says, we might have to consider the possibility of technology, something like thrusters, actively generating each jet. That doesn't prove anything by itself, but those measurements would give us a crucial test. Normal speeds, normal gases, likely a strange but natural comet. Extreme speeds, unusual behavior, we may be looking at something far more advanced than a simple ball of ice. Neptune is drifting, not by much, just a tiny, stubborn deviation over decades, but enough to break the neat, perfect clockwork we thought ruled our solar system. For more than a century, astronomers have known exactly where Neptune ought to be, using the same equations that predicted its very existence back in 1846. Those equations, based on Newton's law of gravity, worked flawlessly, until they didn't. Recently, precise data began to show that Neptune's orbit is ever so slightly off. It's not where our models say it should be. Something is tugging on it, something we can't see. And the unsettling part is, we don't yet know what that something is. A history lesson written in gravity. To understand today's mystery, the story rewinds to the 18th and 19th centuries. In 1781, William Herschel discovered Uranus, the first new planet ever found in recorded history. Until then, humanity believed Saturn was the edge of the planetary system. Overnight, the solar system's known size effectively doubled. Astronomers rushed to track this new world, applying Newton's laws to calculate its path. But Uranus misbehaved. By the early 1800s, careful observations revealed that Uranus wasn't exactly following its predicted orbit. It was drifting slightly ahead of where it should be. The errors were tiny, just a few arcseconds, but they were systematically growing. If Newton's gravity failed for Uranus, it should have failed for every planet, yet it still described Mars, Jupiter, and Saturn beautifully, so something else had to be wrong. Two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, approached the problem independently. They made a bold assumption. There must be an unseen planet beyond Uranus whose gravity was pulling it off course. They tackled what's known as the inverse problem, starting from Uranus's deviations and working backwards to infer the mass and orbit of an invisible world. On 23 September 1846, Johann Galle at the Berlin Observatory pointed his telescope where Leverrier's calculations told him to look. Within an hour, he found a faint blue disk less than 1 degree from the predicted position, Neptune. It was a stunning victory for mathematics and Newton's gravity. We hadn't stumbled upon this planet by accident. We had calculated it into existence. For 107...
Imagine you're watching a galaxy being born. Not through a telescope, but inside a computer. Star by star, supernova by supernova, over billions of years. What you're looking at isn't a science fiction movie. It's a numerical universe. A Milky Way-like galaxy evolving in virtual space, built from raw physics and staggering computing power. You may have seen earlier simulations like TNG-50 from the illustrious TNG project, beautiful, cinematic models of galaxies forming and evolving across the cosmos. These runs helped us understand how galaxies collide, grow, and spin over billions of years. But they were always approximations. They didn't truly follow every single star in a galaxy like our own. For decades, one of the holy grails of computational astrophysics has been clear. Recreate the Milky Way star by star inside a supercomputer. Not just to make pretty visuals, but to rigorously test our theories of how galaxies form and evolve, how dark matter sculpts their structure, and how vital elements like carbon, oxygen, and iron are born in stars and spread through space. Because in those elements lies a deeper question. How did the building blocks of life and worlds like Earth emerge and spread across our galaxy? And if this happened here, where else might it happen? Why simulating the Milky Way is so hard? On paper, the idea sounds simple. Just simulate all of the stars, gas, and dark matter in the Milky Way and let physics do the rest. In reality, the Milky Way contains hundreds of billions of stars. Estimates range from 100 billion up to 400 billion. All of this is embedded in a vast halo of invisible dark matter, swirling interstellar gas behaving like a fluid, and dynamic structures like spiral arms, star-forming clouds, and supernova blast waves. To simulate this properly, you can't just draw stars as dots. Every particle in the simulation must feel and respond to gravity. Gas must flow, compress, cool, and heat like a fluid. Dark matter must clump and swirl according to its own distribution. All of these components interact. This is usually done using techniques like n-body plus smoothed particle hydrodynamics, or SPH. Stars and dark matter are treated as n-body particles, each one pulled by the gravity of all the others. Gas is modeled with hydrodynamics, using SPH particles to track density, pressure, and temperature like a fluid. Then comes the tricky part: scale. Some dark matter structures can extend across hundreds of thousands of light years. Meanwhile, deep inside those structures, tiny molecular clouds form compact clusters of stars in regions just a few light years across. On top of that, you have explosive events like supernovae, heating gas to tens of millions of degrees and rapidly changing local conditions. All in one simulation. So the code must handle huge distances and tiny regions, slow, smooth motions over hundreds of millions of years, and sudden, violent events that unfold over just a few years. This is what's called a multi-scale problem, and it's notoriously hard to compute. Years ago, even simple n-body experiments with a few thousand particles could freeze a home computer. Now imagine trying to model hundreds of billions of them with realistic physics. For a long time, this led to what researchers informally called the billion-particle barrier. Even the most powerful supercomputers were effectively limited to simulations with fewer than about a billion particles. To simulate an entire galaxy, they had to cheat on resolution. One particle might represent not one star, but an enormous cluster of stars, sometimes with a combined mass of hundreds of millions of suns. From afar, those simulations looked like galaxies, but if you zoomed in, the illusion broke. The pixels were huge. You couldn't see individual stars or small-scale processes. The dream of a true star-by-star Milky Way simulation remained out of reach. The supernova problem, time itself becomes the enemy. Supernovae, the explosive deaths of massive stars, are short-lived but incredibly important. In just a few years, they inject enormous amounts of energy into the surrounding gas, stir up shock waves that reshape entire regions, and seed space with heavy elements that will later form planets and eventually life. To accurately track how a supernova affects its surroundings, the simulation has to use extremely small time steps. You can't just say, skip ahead 10,000 years. You'd miss crucial physics. Instead, you might need to step forward in intervals of just a few years or decades to resolve the explosion properly. But here's the paradox. Supernova timescale, years to centuries. Galaxy timescale, hundreds of millions of years for a single rotation of the Milky Way's disk. So every time a star explodes, the entire simulation must slow down dramatically to follow that tiny local event. This constraint is tied to something known in numerical physics as the Courant-Friedrichs-Lewis condition, which basically says your time step can't be longer than the time it takes information, like a shock wave, to move across one resolution element. For simulations, that means if you want high resolution,
and you want fast, explosive events like supernovae, your time steps must be tiny. Tiny time steps plus billions of particles equals a computational nightmare. This is why before 2025, even the most advanced galaxy simulations had to compromise. They could simulate large volumes of space, but at low resolution. Or they could zoom in on small regions with high detail, but only for shorter times or smaller systems. Projects like Illustrious TNG, Eagle, and Magneticum made incredible progress. Illustrious TNG modeled large-scale galaxy formation across the universe's 13.8 billion-year history. Eagle simulated a 300 million light-year cube of the universe using billions of particles to study galaxy assembly. Magneticum focused on cosmic structure, star formation, and chemical evolution, including magnetic fields and black holes. But even these cutting-edge simulations typically stayed below 1 billion particles and worked with coarse particles representing huge collections of stars. The true star-by-star Milky Way model remained unachieved. The James Webb Space Telescope has just reached even deeper into the past than we thought possible. And what it found isn't just surprising. It's forcing scientists to rethink how our universe actually began. To understand why this discovery is such a big deal, we have to rewind
Not 13.8 billion years, but back to 2022. From Hubble's limit to Webb's new frontier. For years, the most distant known galaxy was a tiny, faint smudge called GNZ11, spotted by the Hubble Space Telescope. Hubble, with its 2.4-meter mirror, pushed human vision deeper into the cosmos than any telescope before it. That one little smudge became a symbol of how far we could see. But Hubble has limits. Its mirror is relatively small, and its instruments are optimized mostly for visible and ultraviolet light. To see the earliest galaxies, the ones whose light has been stretched or redshifted by billions of years of cosmic expansion, you need a different kind of eye. Enter the James Webb Space Telescope. Webb doesn't just improve on Hubble, it's in another league. With a 6.5-meter mirror and ultra-sensitive infrared instruments, Webb can catch the faint glow of galaxies that formed when the universe was still in its cosmic infancy, barely a few 100 million years old. Almost as soon as Webb opened its eyes, it started smashing records. One early result was a galaxy named Jade's GS Z14 with a redshift of 14.32. That redshift number tells you how much the universe has stretched the galaxy's light. The higher the redshift, the earlier in cosmic history you're looking. Jade's GS Z14-0 was already breathtaking. We were seeing it as it appeared just a tiny fraction of a billion years after the Big Bang. Then came another galaxy, MOWZ14. Often pronounced like Mom Z14. Its redshift? 14.44. Even further, even earlier. But the real shock wasn't just how far back it was. It's what this galaxy actually is. A tiny galaxy with the power of a giant. MOWZ14 is unbelievably small, only about 500 light years across. For comparison, our Milky Way spans over 100,000 light years. If the Milky Way is a vast city lit from edge to edge, MOWZ14 is like a single blinking block. And yet, this tiny galaxy is blazing. Galaxies this young, this soon after the Big Bang, were expected to be dim and fragile, just assembling their first stars, barely visible even to Webb. Instead, MOWZ14 is bursting with intense star formation, like the universe is running in fast forward. It's not just glowing, it's overachieving. And then there's what it doesn't have. In most star-forming galaxies we've studied, especially those that are bright and active, there's usually a supermassive black hole hiding in the center. These giant black holes control how galaxies grow. They regulate star formation, stir up gas, and can even shut down star birth entirely with powerful outflows. But so far, in MOWZ14, there's no sign of a supermassive black hole. This early, this bright, this active, and yet apparently missing the central monster we expect. Already, that's strange. But when scientists looked deeper, the mystery only grew. Heavy elements where there should be almost none. Webb carries powerful spectrographs, devices that break light into its component colors and reveal which elements are present in the galaxy. When astronomers examined MOWZ14's spectrum, they found something they did not expect. Lots of nitrogen. Not just a trace, strong, unusual levels. This chemical fingerprint looks eerily similar to what we see in some of the oldest star clusters in the Milky Way, places where stars formed in extremely dense environments. And that raises a huge problem for standard models.
In the early universe, galaxies were supposed to be chemically primitive, made almost entirely of hydrogen and helium. Heavier elements like carbon, nitrogen, and oxygen are created inside stars and spread out when those stars die, especially in powerful supernovas. If a galaxy only a few 100 million years after the Big Bang is already rich in heavier elements, that means multiple generations of stars must have already formed, lived, and died. Those stars must have exploded and enriched the galaxy far earlier than our models allow. Galaxy building started much earlier and proceeded much faster than we thought. MOWD14 isn't just a baby galaxy. It's a baby that somehow already looks like it's lived several lives. The little red dots that shouldn't exist. Before Webb, astronomers assumed that such early, chemically rich, compact galaxies would be extremely rare. Maybe so rare that we'd be lucky to find even one. Now, Webb keeps seeing more of them. These galaxies show up as tiny, bright, reddish specks in Webb's deep images and have earned a nickname, little red dots. They're small, extremely compact, surprisingly bright, rich in heavier elements. MOWZ14 might be one of the most extreme examples we know, but it's clearly not alone. If galaxies like this are common in the early universe, our entire picture of how structure formed may be incomplete. Instead of a slow, gradual buildup of simple, small galaxies, the infant universe might have been a wild, hyperactive workshop, rapidly assembling dense, enriched star-forming systems much earlier than expected. Does this break cosmology? Not exactly, but it absolutely stretches it. Current models say early galaxies should be rare, small, chemically simple, and relatively faint. MOWZ14 checks only the small box. It's bright, it's chemically evolved, it's furiously forming stars. It's everything we didn't expect this early. That means the basic framework may still be right, but the details, the timings, the rates, the assumptions need serious revision. In other words, the puzzle pieces haven't been thrown out. We've just discovered that the picture on the box was incomplete. New eyes on the ancient universe. The James Webb Space Telescope is only the beginning. Soon, the Nancy Grace Roman Space Telescope will join the hunt. While Webb focuses like a spotlight on small regions with incredible depth, Roman will act more like a wide-angle panorama camera, covering huge swaths of sky with high sensitivity. Together, Webb and Roman could discover hundreds or even thousands of galaxies like MOS-14 scattered across the early universe. Each one is a breadcrumb from a time when the cosmos was less than 1 billion years old and light was just starting to break through the cosmic dark ages. Every one of these objects tells us the early universe wasn't just slowly waking up. It was already buzzing with activity. But the surprises don't end with galaxies. As Webb and other surveys refine our cosmic map, some scientists are asking a deeper, more radical question. What if our universe itself isn't what we think it is? A universe inside a black hole? Alongside Webb's discoveries, another line of research is quietly stirring debate. Astronomers have been studying the rotation of galaxies across the sky, looking at which way their spiral arms curl and how they spin. If the universe is completely random and symmetric on the largest scales, you'd expect roughly half of galaxies to rotate one way and half the other. But that's not what some studies are finding. Instead, there appears to be a small but persistent imbalance. More galaxies seem to spin in one preferred direction than the other. This kind of asymmetry is called anisotropy, and it clashes with the standard assumption that on large enough scales, the universe looks the same in every direction. That weird twist has led some researchers to a daring idea. Maybe our universe exists inside a black hole. This concept, often called black hole cosmology or Schwarzschild cosmology, proposes something bold. Our entire observable universe. When the James Webb Space Telescope first unfolded its golden mirrors in space, astronomers thought they knew what was coming next. Sharper images, cleaner data, a better look at the young universe. They did not expect it to start quietly poking holes in one of the most sacred assumptions in cosmology, that on the largest scales, the universe looks the same in every direction and follows the same rules everywhere. Yet, that's exactly where Webb's discoveries are leading. Webb's early shock, the universe isn't behaving. Within its first year of operation, Webb began finding galaxies that simply shouldn't exist, at least not so soon after the Big Bang. They were too massive for their age, too well organized with clear structure, too bright, forming stars at astonishing rates. At first, these results were celebrated as a triumph. Webb was doing exactly what it was built to do, revealing details that Hubble could never see. But then something more troubling emerged from the data. When scientists used Webb to measure how fast the universe is expanding, the numbers weren't lining up. In some directions, or using some methods, the expansion appeared slightly faster than our standard model predicts. In others, it matched or lagged behind. Tiny differences, measured in just a few kilometers per second per megaparsec, but differences that refuse to disappear. Suddenly, this wasn't just about early big galaxies. It was about something much deeper. Is the universe really as uniform as we thought? Back to the beginning. Hubble, expansion, and the Big Bang. To understand the problem, we have to go back almost a century. In 1929, Edwin Hubble discovered that distant galaxies are all moving away from us. The farther they are, the faster they recede. Their light is stretched into longer, redder wavelengths, a phenomenon now known as redshift. This simple relationship, now called Hubble law, led to the idea that space itself is expanding. If everything is moving apart today, then in the past, everything must have been closer together, denser, hotter. That's the foundation of the Big Bang model. For decades, astronomers measured the expansion rate of the universe, known as the Hubble constant, using two main approaches. The local universe, measuring distances to nearby galaxies using standard candles, like Cepheid variable stars and Type A supernovae. These objects have predictable brightness, so their apparent dimness tell us how far away they are. The early universe, studying the cosmic microwave background, the faint afterglow of the Big Bang. Missions like WMAP and Planck converted this radiation pattern into a prediction for how fast the universe should be expanding today. If our understanding of cosmology is correct, both methods should give the same number for the Hubble constant. They don't. The difference is small, but stubborn. Local measurements suggest the universe is expanding faster than the early universe prediction. This conflict is known as the Hubble tension. Webb was supposed to help decide which side was right. Instead, it made the tension even sharper. Webb's deepens the Hubble mystery. Webb can see fainter, deeper standard candles than any telescope before it. When astronomers used Webb to recheck distances using distant supernovae, Cepheid variable stars and galaxies farther away than Hubble could cleanly resolve, they found that the local expansion rate is indeed higher than what we infer from the cosmic microwave background. In other words, the problem isn't going away. It's getting harder to ignore. Nobel Prize-winning astrophysicist Adam Rees, who helped discover the accelerating expansion of the universe back in 1998, has described the situation as both exciting and unsettling. If this discrepancy holds up, it's not a minor calibration error. It's a signal. A signal that something fundamental in our model of the universe is missing. Possible explanations range from bold to wild. Maybe dark energy, the mysterious ingredient causing cosmic acceleration, doesn't stay constant over time. Maybe the geometry of space isn't perfectly flat and uniform the way we assumed. Or maybe something even stranger is happening. Perhaps time itself doesn't